Section 3.3. 3.3 is the derivative rules that you have to memorize and know by heart. There is no cue cards on this exam. No cue cards. This is for your ability to Cal 2, Cal 3, differentials. When you do take that, because if you're engineering or math majors, differentials and combinatories. So it is a crucial, and statistics. The statistics we teach is not calculus based, but the statistics you need is calculus based because we test the validity of means and calculus. So derivatives are going to be very functional, and it's crucial for you to know these rules by heart. They're not difficult, and come up with a mnemonic if you can. That's how I survive these, and it'll work. So first off, we're going to start with converting root values in terms of exponentials. And that's to understand that we can change any index to a fraction. So in this case, the 4 is a multiplier, and then we have x to the 8 divided by 5 because this guy is an index. Is everybody comfortable with that? In this case, we notice we have the parentheses around the entire radical. And it is raised to the 7th power, and it's part of 13. So we're going to put the 7x 8y, which is the radical, the radicand, in the radical, and then put to the 7/13. Does everybody see that? I don't know. When I type this stuff up, whole thing is raised to the 7, and the radical, the index, applies to everything within the radical. Is everybody good? Because this way we can distribute it in there and do some quick and dirties. All right. Okay. Now we're going to review what a derivative is. The definition of a derivative is the limit f prime of x, the limit as h approaches 0 of the difference quotient. The functional inclusion of a change of x. Sorry about that, I don't need a square there. Sorry. Minus the original function divided by h, where h is canceled out. Tangent point at a point, that means that we want f prime of the x of the point, slope, and then we do our equation of the line y equals in parenthesis x minus that x sub 1 plus the y sub 1. This one being our point. All right. Those are the background. Okay. So our first derivative is of a constant, and we know it's going to be d over dx of any constant is always 0. In other words, the impact of that is a vertical movement to the function, so it's not critical. Then we have this one, the power rule, and they use it as a positive. It doesn't matter. You just have to carry the sign with it. Okay, so the dx of x to the n is x to the n minus 1 and times the n times x. And so we're saying what we did on that one, we cheated because it was ugly. I don't want to do it. Okay. The next one is a distributive process of two indistinct terms with x involved or x not involved, it doesn't matter, that we take each term and take the derivative. Now, let me say it again. we take each term in that polynomial and take the derivative. Is everybody comfortable with that? Okay, so it says dx of u plus v is the derivative of u plus the derivative of v. Okay, that each term within the plus or minus, again, plus or minus, is that process. So we're going to do some examples. So this one is our sum rule. So if I have s equals to 8t to the fourth minus 4t to the eighth, then I know that ds dt, again, the independent variable is always attached to the denominator reference. It's going to be very valuable later. So, okay. So we're going to have 4 times 8 is 32, t to the 4 minus 1 minus 32, t to the 8 minus 1. Questions? Now this one is tricky. Why is this tricky? It's a sum rule. Why is that one tricky? Okay. Okay. It is the sum rule. All right. So we're saying that ds dt is going to be 8/3 times 6 t 8/3 minus 1 plus what? That term. What is this term? What is it? Am I asking an unfair question? I'm sorry? Yes, exactly. E is a number. There's no variable. Don't get me wrong, we're going to have variables in E, but this one does not. So this is a plain old constant, and I'm so proud of you. And the derivative of constant is 0. Is everybody comfortable with that? I'm going to simplify. I know your eyes are just like scared about this. Is everybody comfortable with that? All righty then. Now here we have a variable. And in this variable, we treat it the same way. We take the derivative of that. But we understand that the derivative of e to the x, singular x, is e to the x. So any e up there is initially what it is. But then we have to take the derivative of whatever numbers attached to that x, or power rule attached to it. And then it gets kind of convoluted with everything else we've learned. So, so we're going to talk about that. So e to the x is e to the u du. Du meaning derivative of whatever that exponent is. That it should have written it with the chain rule involved in order to make sure that you don't lose track of what you're doing, you know. But, so I put it in. This is if we have a number or a power onto that x variable, okay? Is everybody comfortable with that? Okay. And I put it in there so I wouldn't forget. So in this case, the first step would be rewrite. Right. So in this case, we're using first the sum rule. and natural log. Okay, so in this case, if I want dy dx, then I'm going to multiply by 3, and that gives me a 5x to the second, right? Because we subtract 1. All right. This is, what if I take 1 from x, what do I have? X to the 0. What is x to the 0? 1. Any number to the 0 is 1. Y'all remember, I gave you those rules, yes? Okay, so just so you know, I'm going to have a negative 7 plus 9e to the x, because it's just e to the x, and 9 is a multiplier, doesn't have a, and this is our solution. Is everybody good? Now we have a variable with a coefficient. All right, so now we have e to the u derivative of that exponent. Okay? All right, and we got 2 of them that have that. So if I'm doing this one, I'm going to have a negative 4e to the negative 4. This guy doesn't change, but the negative is there because we have x to the 1 minus 1. Does everybody understand that? Having to be a negative 1 times an x to the negative. So it's negative 1. Is everybody good? Did I lose anybody? All right. Now that takes care of that part. So then I have plus 3e 3x. Derivative of that 3x is 3. Questions? All right. So what is my solution? dy dx equals negative 4e to the negative. Because of this, we have this. Yes? Plus 3e to the 3x. Because of this, we have that. Yes. Outstanding. The product rule. Oh my God. That we can't do FOIL and make it a polynomial. Does that make sense? If it's ugly, then we have to use this guy. Now, if you can do FOIL, then do it and then do each term. But if you can't, because it's ugly, then have to use this. This one says, but now remember, we're talking terms. We're saying the u term times the d dx of the v term plus the du dx of the first term times the second term. First, and I do it wrong, so derivative of the second times the first plus the derivative of the first times the second. Comfortable with that? Right. So we're going to apply this product rule to this guy. Now, we could do FOIL on it, but it's ugly. You know, it's a lot. And we could make a lot of mistakes because it's a 3-term times a 2-term. So it's kind of, let's just bite the bullet. Okay. Everybody see that? I took the derivative, the u times dv. I'm going to put a plus. Now I'm taking the derivative of u, which is a negative 2x times the v. All right. There's a lot of math on these, and you try to look for commonality if possible, but this one doesn't. Well, I'm going to have to do some math. It's okay. All right. I can breathe. So I'm going to have 3x squared minus 5 and 6 minus x squared. All right, so I'm going to have 18x squared minus 30. And then on this one, I'm going to have a negative 3x to the 4, negative 5x squared. It looks like 23. I don't know how the computer wants it, so I might be doing, but because this is a single that I have to distribute, I'm pretty sure we had to do math because it's probably going to all combine a little bit, So this is going to be a negative 2x to the 4, a positive 10x squared, and a negative 10x. Does everybody agree with that math? All right, let's see what we have. I have a 4, so that's going to be 5x to the 4th because I'm combining like terms. Everybody good with that? I'm going to have an x squared, a 23x squared, and a 10 squared. So that's going to give me plus 33x squared. Then I have a negative 10x and a negative 30. Questions on that? Please check my mind. I'm going fast, so. Questions? A little involved, not scary involved. Like I said, if they're small, do FOIL and take the derivative of a polynomial every term. But this one was not. A lot of it was yuckies. This is the one that gives a headache to all of young mathematicians in Cal, and that's the quotient rule. It's the derivative of the top times the term of the bottom minus the derivative of the bottom times the top. And that's all over the bottom squared. That's how I remembered. That's when I tutored. That's what I told them, because multiplication is commutative. And once you simplify that numerator, it doesn't matter what you did first or second. But derivative is the first important part. We take the derivative of the top first, then multiply by the bottom term. Then we do subtract the derivative of the bottom times the top term all over the bottom square. Everybody comfortable with that? Pretty yuck, but not bad. All right. These are terms, and it wants first and second derivative. So now when we talk about second derivative, we're talking f double prime, or d squared y over dx squared, or any letter, and double is like that for the dy dx. All right. And in this one, it's r. So let's see what we want to do. Do we want a common denominator, or do we want to take the terms individually? Individually? Is that what you said? Okay. On this one, it's s to the 4 and 15. So if I did that, then this top one would be 5s squared. And this one would be 3 times 8. I don't know. It doesn't matter to me. Say something. What do you want?
Let's do it together.
Together? Okay. We're looking for a common denominator of 15s to the 4th. 15s to the 4th. We're not changing anything, making a common denominator. Is everybody good? Everyone okay? Alrighty then. Here we go. So we're going to do the ds, first start. Okay. And that's going to be derivative of the top times the bottom. Minus derivative of the bottom, which is what, 60, times the top, over the bottom squared. All right, now we're going to do some math. Not a big deal. And this is an S, not 105, just so you all know. So I'm going to have 150 S to the 5 minus, and I'm going to do distributive. That's 300, yep, S to the 5 plus, I don't know what that is. I'll make a mistake for sure. That is 24 times 60. 1440. And that's it's a plus because it's a negative negative, S to the 3rd over the bottom. Oh, 15 squared is what, 225? Yes? That's going to be S to the 8. All right. Almost there, guys. Okay. I have these two together, and I'm going to have a what? A negative 150 S to the 5. All right. So I have a S to the 3rd that's common, and I guess a 5, or I don't know if I can do, this one's kind of interesting. I'm going to divide. Let me see what it comes out. Yep. And a 15. 150, right? No, 15. I'll do 15 first and then figure out. So I'm going to put, sometimes the leading coefficient of negative is removed, but it doesn't matter if you take it or not. I don't believe. So I'm going to say 15 S to the 3rd. And I said this was 96. All right. When I cancel this 15, right? Because 225 is going to have 15, I think. Yep. I'll get 15 S to the 5. So now I have it. because it makes it easier to do the second derivative. Is everybody comfortable with that? Check my math. I think I'm good. All right, so we're going to do second derivative. Okay, and the second derivative, we start with our drdt. Yes, I'm sorry. All right, here we go. In this case, we're going to take the derivative of the top, which is negative 20s, and the derivative of a constant is 0, times the bottom, minus the derivative of the bottom, what is that, 75s to the 4, times the top, all over the bottom squared. All right. Okay, so I've got 300 negative, right? S to the 6. Minus, and that is 750 S to the 6, minus, oh no, that's a plus, sorry about that. Plus, minus, oh, I don't know what that is. With that, I got the first one because that was easy, 10 times 75. But 96 times 75 is a little different, 7,200, and that's a plus, 7,200 with an S to the 4. All right, so I'm going to do a little bit cleanup. And I've got a negative 300 and that, so that's 450 positive, plus the 7,200 S to the 4, all over the 225 S to the 10. Okay, is that divisible by 15? Okay, so we can do a 15. Yes, okay. And we'll probably be able to do a little bit more. Okay, so I'm going to do S to the 4. Oh, sorry. Okay, when I cancel this guy, I'm going to have 15 S to the 6. Does everybody see that? Anybody away? Okay. And this is 12, so it can be a 3. Yeah, we can do a 3. All right, we can go further. These are multiples of 3. And this is 3 and 5, so we can do the 15. Maybe, maybe. Yeah. I didn't see it at the beginning, and I'm sorry. Little bit math. All right. This is our quotient rule. I think I always do a lot on the quotient rule because if I say it enough, some of it will stick. Could be true, could be false, I don't know. That's my logic. So we want only the derivatives, not the second. I think you have two going to the second. One of them a polynomial, big polynomial, and the other one is a quotient rule. Okay? I don't think I did any product rule. Okay. Derivative of the top times the bottom minus a derivative of the bottom times the top all over the bottom squared. All right. So I'm going to have 10x minus the 35 minus 10x minus the 16 all over. Okay, when I did that, I have additive inverses and then adding. Negative 35 and negative 16 is like 51, right? Questions? All right, we'll give this one a shot. These are squares. And we know this guy has a horizontal with y equals 8, don't we? Yeah, okay. Find the derivative of the function. That means when they ask for a derivative, they're saying the rule that you find the three items that I mentioned. Okay, this is the rule that'll work to find, so long it exists in the function. Of course, this one, it won't exist across that 8. Okay, here we go. Right. So we're saying dy dx is going to be derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. All right, we're going to do some distributive property. Is going to be 16x to the third plus 16x. A distributive property minus 16x to the third minus 10x. All over the bottom squared. So we notice the 16x cubes are additive inverses, and then we have common values of 6x over x squared plus 1 squared. Okay, this is the first and second derivative. And we notice on this one that we can divide through that concept, okay, because we have a singular x. So I would simplify it. Because we know this guy is a negative 1 over x squared. This case. Okay, does everybody see that? And then we can do the derivative of that. And I did that one as an example in the top, in the previous lesson, saying it's 5 times 1 over x, and 1 over x is a negative 1 over x squared. Okay, I didn't want to, like, oh, she made that up. No, I didn't make it up. Again, look, your math confidence is what, and your vision can make it easy or it can make it more directed. And I always ask you which way you want to go. It's going to work no matter which way you go. Is everybody comfortable? Questions on that? Oh, I'm sorry. Questions? Oh, I have a second derivative. I'm glad I looked. Now, depending on your abilities, negative exponents. And this one lends itself to that. Okay? Your math prowess is always your friend. And if you go to Ash, that's what she does. She doesn't deal with the quotient rule if there's a single value in the denominator. And that's what I have here. So I'm going to write it like this. Make it a polynomial look. All right. And you can do in mathematics anything that's mathematically sound. And what would be the less of the issue, right? Less of an issue. Okay. And I'm going to have 8x plus 10x to the negative 3 because I take away 1. Yes? So, ta-da! Oh, yes. And if you did the quotient rule, you'd end up with an x in the numerator and cancel one of the x, because it would be the bottom squared, and you would have canceled. We would have gotten a third cubed in the denominator. Questions? So we used a lot of intuitive application of what we know, right? Okay. All right, now we're getting to the fun part. Let me stop this.